The National Electrical Code (NEC) dictates many aspects of electrical installations, including underground services. It's essential to understand the specific requirements in place at the time of installation, as codes evolve over time. Regarding expansion couplings for underground residential services, the NEC did not mandate their use prior to 1996. This means that a residential service installed in 1994, according to the NEC alone, wouldn't have been required to have expansion couplings. However, relying solely on the NEC may not provide a complete picture. Individual states or even local jurisdictions often have the authority to amend or supplement the NEC with their own regulations. These local codes can be more stringent than the NEC, imposing additional requirements not found in the national code. Therefore, it's possible that Massachusetts, or even the specific town or city where the house was built, had local amendments to the NEC that required expansion couplings in 1994, despite the NEC not requiring them until 1996. To determine the definitive answer for this particular installation, it's crucial to consult the local building code or the electrical inspector's office that had jurisdiction over the area in 1994. These resources would hold the specific regulations enforced at the time. The absence of expansion couplings, if they were indeed required by local code, could contribute to the sinking and pulling away of the service from the house. Temperature changes cause expansion and contraction in materials like PVC conduit. Without expansion couplings, this movement can exert stress on the conduit and connections, potentially leading to issues like sinking or separation. The purpose of expansion couplings is to accommodate this thermal movement, preventing stress and damage to the system. They essentially provide a flexible joint in the conduit run that can expand and contract without putting pressure on the surrounding components. When investigating issues like this, a layered approach is necessary. Firstly, understand the NEC requirements at the time of installation. Secondly, research any local amendments or regulations that might have been in effect. Thirdly, visually inspect the installation for any signs of damage or improper installation. And fourthly, consult with qualified professionals, such as electrical engineers or inspectors, to assess the situation and provide recommendations. If it turns out that expansion couplings were required but not installed, remediation may be necessary. This could involve retrofitting expansion couplings into the existing conduit run or, in more severe cases, replacing sections of the underground service. The specific course of action will depend on the severity of the problem and the recommendations of a qualified electrician. When planning and executing any electrical work, safety should always be the top priority. Working with underground services can be hazardous, so it's crucial to take appropriate precautions. This includes energizing the circuit, using proper personal protective equipment, and following all applicable safety regulations. Always consult with a licensed electrician before attempting any electrical work. They have the knowledge and experience to perform the work safely and correctly. In addition to the NEC and local codes, manufacturers' instructions also play a role in proper installation. Conduits and expansion couplings come with specific instructions for installation, including proper spacing, support, and sealing. Following these instructions is essential for ensuring a reliable and long-lasting installation. Failure to adhere to manufacturers' instructions can void warranties and potentially lead to problems down the road. Therefore, it's important to review and understand the manufacturer's instructions before beginning any installation work. The sinking of the underground service could also be related to soil conditions. Unstable soil or poor compaction can cause the conduit to shift and settle over time. In such cases, it may be necessary to address the soil issues in addition to any electrical repairs. This could involve compacting the soil, installing retaining walls, or improving drainage. A geotechnical engineer can assess the soil conditions and provide recommendations for stabilization. Another factor to consider is the depth of the burial. The NEC specifies minimum burial depths for underground services depending on the voltage and the type of location. If the conduit is not buried deep enough, it may be more susceptible to damage from surface load or frost heave. Frost heave is the upward swelling of soil due to the formation of ice. This can exert significant pressure on underground structures, potentially causing them to shift or crack. Ensuring that the conduit is buried at the proper depth can help to mitigate these risks. Furthermore, proper backfilling is crucial for protecting the conduit from damage. The backfill material should be free of sharp rocks or debris that could puncture or crush the conduit. It should also be properly compacted to prevent settling. Improper backfilling can create voids around the conduit, which can weaken the system and make it more susceptible to damage. In summary, determining whether expansion couplings were required in 1994 in Massachusetts for underground residential services requires consulting the local building code or electrical inspector's office that had jurisdiction at the time. While the NEC didn't mandate their use until 1996, local regulations may have been more stringent. The sinking and pulling away of the service could be related to the absence of expansion couplings, soil conditions, improper burial depth, or improper backfilling. A thorough investigation by a qualified electrician is necessary to identify the root cause of the problem and recommend the appropriate course of action. Remember to always prioritize safety when working with electrical systems and to consult with qualified professionals for any repairs or installations. The NEC, or National Electrical Code, serves as a foundational standard for electrical safety in the United States. However, it's essential to recognize that the NEC is not a static document. It's revised and updated every 3 years to incorporate new technologies, address emerging safety concerns, and improve the overall clarity and effectiveness of the code. These updates can have significant implications for electrical installations, so it's crucial for electricians, contractors, and inspectors to stay informed about the latest changes. The process of updating the NEC involves a rigorous process of review, public input, and consensus building. The National Fire Protection Association, NFPA, which publishes the NEC, solicits proposals for changes from a wide range of stakeholders, including industry experts, manufacturers, regulators, and the general public. These proposals are then reviewed by code-making panels, which are composed of experts in various areas of electrical safety. The code-making panels consider the technical merits of each proposal, as well as the potential impact on safety and cost. They then develop revisions to the NEC, which are subject to further public comment and review. This iterative process ensures that the NEC reflects the best available knowledge and practices in the field of electrical safety. One of the key principles underlying the NEC is the concept of approved. The NEC frequently uses the term approved to refer to equipment, materials, or methods that have been found to be acceptable by the authority having jurisdiction (OJ). The AHA is typically a local electrical inspector or building official who is responsible for enforcing the NEC and other applicable codes. The AHA has the authority to determine whether a particular installation meets the requirements of the NEC and is safe for use. The definition of approved can vary depending on the jurisdiction. In some cases, the AHA may rely on listing and labeling by a nationally recognized testing laboratory, NRTL, such as Underwriters Laboratories, or Intertek et.al. NRTLs test and certify electrical equipment to ensure that it meets applicable safety standards. Equipment that is listed and labeled by an NRTL is generally considered to be approved by the AHA. However, the AHA may also have additional requirements or may conduct their own inspections to verify compliance with the NEC. The NEC also addresses the issue of grandfathering. Grandfathering refers to the practice of allowing existing installations to continue to operate under the code requirements that were in effect at the time of installation, even if those requirements have since been updated. The NEC generally allows grandfathering, but there are some exceptions. For example, if an existing installation is deemed to be unsafe or a hazard to life or property, the AHA may require it to be brought up to current code standards. Additionally, if an existing installation is undergoing significant renovation or expansion, the AHA may require the entire installation to be brought up to current code standards. The concept of grandfathering can be complex and is often subject to interpretation by the AHA. It's important to consult with the AHA to determine the specific requirements for any existing installation. The NEC also includes provisions for special occupancies. Special occupancies are locations that have unique electrical hazards or requirements, such as hospitals, theaters, and hazardous locations. The NEC provides specific requirements for these special occupancies to address the unique risks they present. For example, hospitals have strict requirements for emergency power systems to ensure that critical life support equipment continues to operate during power outages. Theaters have requirements for fire alarm systems and emergency lighting to ensure the safe evacuation of occupants in the event of a fire. Hazardous locations, such as chemical plants and refineries, have requirements for explosion-proof equipment and wiring methods to prevent igniting flammable gases or vapors. The NEC also addresses the issue of voltage drop. Voltage drop is the decrease in voltage that occurs along a conductor due to the resistance of the conductor. Excessive voltage drop can cause equipment to malfunction or fail to operate properly. The NEC provides guidelines for calculating voltage drop and recommends that conductors be sized appropriately to minimize voltage drop. The NEC recommends that voltage drop on feeder conductors not exceed 3% and that voltage drop on branch circuit conductors not exceed 5%. The NEC also includes provisions for grounding and bonding. Grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to flow back to the source, which helps to trip over current protection devices, such as circuit breakers and fuses, and to energize the circuit. Bonding connects all metal parts of an electrical system together to create a lower impedance path for fault current. This helps to prevent electrical shock hazards. The NEC provides detailed requirements for grounding and bonding, including the size and type of grounding conductors, the methods of connecting grounding conductors to equipment, and the requirements for grounding electrodes. The NEC also addresses the issue of overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. Overloads occur when a circuit is carrying more current than it is designed to handle. Short circuits occur when there is an unintended low resistance path for current to flow, such as when a wire comes into contact with a grounded metal object. Overcurrent protection devices interrupt the flow of current when an overload or short circuit occurs, preventing damage to equipment and reducing the risk of fire. The NEC provides detailed requirements for overcurrent protection, including the size and type of overcurrent protection devices, the location of overcurrent protection devices, and the requirements for coordination of overcurrent protection devices. The NEC is a complex and comprehensive document that covers a wide range of electrical safety topics. It's essential for anyone involved in electrical work to have a thorough understanding of the NEC and to stay informed about the latest updates. Consulting with qualified professionals, such as electrical engineers and inspectors, can help to ensure that electrical installations are safe and compliant with the NEC.